We're going to discuss MRAM, magnetic random access memory. So this is one of the emerging non-volatile memories. First, we will discuss the principle of the MTJ, magnetic terminal junction, and then we will discuss three kinds of MRAM device structures. First is the field MRAM, second is STT-MRAM, third one is SOT-MRAM. So first of all, the MRAM is based upon this so-called MTJ, magnetic terminal junction. So it's a three-layer structure, and we have two ferromagnetic layer. You can think this is a little magnet. And then the two layers of the ferromagnetic material separated by this ternal oxide. And this is typically made of the MgO structure. So the two ferromagnetic layer, the properties are different. So here the bottom one is called pinned layer. In this case, the magnetization direction is pinned in this example always to the right. So you think this is a magnet, right? You have the north pole, south pole. So then this one is always pinned to the right. And then the top layer is called a free layer. In this case, it can switch between the left and the right in terms of the magnetization direction. And as we briefly discussed before, for those two configurations, if the two layers are in the parallel states, their resistance, if you measure the resistance across this stack, the resistance in this parallel state is smaller than the configuration where the two ferromagnetic layers are in the anti-parallel state. So the resistance is different. So this is the basic property of this MTJ structure. You have two little magnets, depending on their magnetization direction, parallel or anti-parallel. Then you will have different resistance across the stack. Or in other words, if you read out the current through this vertical path, your readout current will be different. And actually, the MTJ structure is very complicated to be fabricated. So here, this is the schematic for the complete MTJ structure. So here, the core is this three-layer structure, which is here. So this terminal barrier is like the MgO, as we discussed before. And then we have the bottom like reference layer or pinned layer, and the top like free layer. But typically, the materials here are associated with like cobalt, iron, and boron. So this is the typical like magnetic material. But to make the bottom pinned layer to be always pinned, so there will be like some assisted layers. So those layers will help to pin the bottom layer, for example, always to the right. Oh, so this is the so-called, sometimes called the SAF structure, a synthetic antiferromagnetic layer. Oops. To help to pin the layer. So it's very complicated in terms of the structure you have to fabricate. So you have to deposit multiple very thin layers in the sputtering process. And typical thickness of each layer is only like a few nanometers. So you only have a few, maybe tens of angstroms, tens of atoms in the thickness. So it's very precise deposition to make this MTJ structure. So here the MTJ current conduction is governed by this spin-dependent quantum tunneling. So here are some device physics. So basically, in the magnetic layer, the magnetization actually is caused by the spin state. Spin is some inherent property of the electron. So the spin up and spin down are the two basic states. So you can think the electrons is rotating by itself. It's not accurate to describe that, but you can think the electrons is rotating, like the Earth is rotating. So you have the spin up and spin down, depending on the rotation direction. It's not accurate to describe like that. What is the spin? It's not accurate, but to the first order, you can think like that. So the no resonance state. So basically, the two magnetic layer will have the same direction, the parallel state, and in this case, the electrons in those two layers will have both electron like spin up and spin down. So here, this is the energy diagram. So basically, the EK relationship, the energy. This is like a density of states. So basically, here is the occupancy of the electrons. So here, if you apply voltage to the right, then you're going to push down the band. And then for the spin down electrons, they will turn through this oxide layer. And then spin up will also turn through. So in the parallel state, so here the density of states is the capability for the material to hold the electrons. Therefore, here you have the matched configuration. You have more electrons in the spin down, and then here you have more states to accept the spin down electron. So you have large current. But in the anti-parallel state, then because this side is anti-parallel, and that means you have less states to hold the spin down and more states to hold the spin up. And in this case, if you apply the voltage here again, then the electrons will turn through, but the turning probability will be lower. The reason is that here, from the left-hand side, you have more spin down electron, but you have less empty space to accept those spin down electrons. So therefore, the current is lower. So in the magnetic material, so for the spin up and spin down, so it's always like the spin up states will accept the spin up electron, and spin down states will accept the spin down electrons. So this is the origin of this magnetic state dependent quantum tunneling, and you have the two different states. I don't require the detailed physics here, so this is just for your information. But again, what is important is there is a resistance ratio between the high and low resistance states. And actually, you can trigger the magnetic switching by applying external magnetic field. So here, those two states, right? And if you measure the resistance change across the stack, you can apply, for example, the magnetic field pointing to the right to switch. This is always pinned, right? The bottom one pinned, and the top one is free. So if you apply very magnetic field externally to the right, then you're going to flip the top layer to the right, and then you have a lower resistance here. This is the resistance ratio. If you make it like a reference, this is 0. Like the resistance difference or the change, if you make it as the reference, Then if you switch the magnetic field to the left on the negative side, then you are going to make them anti-parallel, and then the resistance will change by like 120%. So here, this TMR ratio, tunneling magnetoresistance ratio, is defined as the resistance of the anti-parallel state minus the resistance of the parallel state, basically the delta R, the change, divided by the reference, which is this RP, the parallel state resistance. And actually TMR 100% means on-off ratio is 2. Why is that? If you think the RP is 1, let's say you normalize that to 1, for example 1 kilo ohm, and then the RAP is like 2 kilo ohm, then it's like 2 minus 1 divided by 1. So this gives you 100% TMR ratio. But actually, in terms of on-off ratio, it's pretty small. If you compare this number with other non-volatile memories we discussed before, like RRAM phase change, the on-off ratio can be up to like 10 or even sometimes 100. So the MRAM, the MTJ resistance difference is pretty small. It's like only 2 on-off ratio. So sometimes they translate that to this 100% TMR ratio. So it's a pretty small ratio, and this is actually very challenging for the sense amplifier to distinguish the differences because the changes are so small. Although it's like 100%, but actually, you know, this is just a 2, like 1 kilo ohm versus 2 kilo ohm. So your low resistance state is like 1 kilo ohm, your high resistance state is like 2 kilo ohm. So it's pretty small change. And here, this is the magnetic field trigger switching. You need to apply external magnetic field. Of course, in practice, in the real circuit, you won't have the external magnetic field. This is for testing purpose. When you make the real integrated circuit, you cannot rely on external field to switch. And in the past 20 years or so, the MTJ ratio keep increasing through the stack engineering, and this MTJ resistance change was discovered in 1990s, and then over the few years, the magnetic the TMR ratio increases, and typically today is like 100% to like 120%. And through like special engineering, it can be further improved. And the record is like 600% TMR ratio. But for the practical MRAM devices, typically what the industry use is like maybe 100% to 150%. The on-off ratio is like 2, at most 3. Okay, so then let's discuss how we integrate the MTJ to a memory structure. So the first one is called this field switching MRAM, magnetic random memory. So in this case, this is the MTJ stack, and we need to add a read transistor, selection transistor here, and then here there's a write word line. So here there's a write word line underneath the MTJ, and there's a isolation layer in between. So here there's isolation. So here we didn't draw it out, but there's isolation in between. And then we have the bit line here. So we have 2 word lines. One is the read word line to control the transistor. So in the read, it's like 1T, 1R. It's like 1T, 1R, as we discussed before. For the write, then the write signal is going to apply to this write word line, which is directly underneath the MTJ, but separated by the isolation layer here. So we will discuss the switching mechanism for this so-called field switching field switching MRAM in the next few slides. So this is field switching. We will discuss why this is field. And then later the STT-MRAM, which is more industry friendly today is directly the 1T controls the 1R. And the read and write will share the same word line. So there's no separate write word line. And we will discuss the STT-MRAM later. So let's look at the first generation, the field switching MRAM. This was the first generation developed in the early 2000s, the field MRAM. So this is like a cross-sectional view of the field MRAM device. You have the transistor underneath, 1T. This is a transistor, right? And then go through the metal wire, like the contact wire. You make it up. And then here, this is MTJ structure. You have two magnetic layers and separated by this internal barrier. So here, this right wire line is a metal line, right underneath the MTJ, and then here there's isolation in between. So this is the structure for the field switching MRAM. And here is some real image of the fabricated chip, I believe from IBM. So here, this is a real image. Of course, this is in the early 2000s. So the transistor size is a little large. But anyway, so here is a CMOS transistor on the substrate. And then you have the metal wire. And then here, MTJ is here. And then this is the right wire line. So let's discuss how it switches. So basically, if you look at this structure, it's not cross-point array, because here this is like your memory cell, and then you have the horizontal bit line, and then you have the right wire line, this WWL in this image should be in and out of the plane. So it's hard to draw, but you can think this right wire line is in and out of the plane. And then you have the bit line. So for the write operation, this is like a cross-point array. The only trick here is that this is isolation here. So this right wire line does not directly interface with the memory cell. Then how would it switch? Then the trick is the field switching. Field means magnetic field. So if you think the simplified cartoon figure like this, right? So this is like your bit line, and this is like your right wire line. Let's say this is a bit line, and this is your right wire line, WWL. And this is underneath, this is selected cell in the memory array. So they don't interface directly. However, when you apply the AC current, right? If you apply current, if you recall your college physics or even high school physics, the current, if you have alternating current, you will generate the magnetic field around the current, following the right hand rule, right? Right hand rule. So if you apply current this way, then you use the right hand, and then you will have the circulating magnetic field associated with that current. So you see, if you apply two right currents like this, then you are going to have this oscillating field, magnetic field, and that field can switch the MTJ, the free layer. So you rely on the field generated by the current to flip the MTJ in this case. So it's field switching. And again, you will have this so-called half-selector problem, right? Because here you want only this cell to be flipped, so you need to apply both currents from the right wire line and the bit line. And then this cell is going to experience the both field. This field will be perpendicular. One is like you are going to have this, for example, you are going to have this direction and that direction. So effectively, then you will generates a combined field pointing to this direction. And this one probably can switch the magnetic terminal junction to the right. And then if you want to switch to the left, then just need to reverse the WWL direction. For example, you reverse it, then you still applying the BL, so you have this field and this field. So effectively you have this field. This will switch this to the left. And this is for the selected cell. And for the other half selected cell along the same column or along the same row, then you will only have one, for example, one of those field. And the assumption is that one of those only will not flip the half selected cell. It's like you apply the half-way bias, right? You need the both field to flip that, and half of that will not flip. So that's the assumption for this field switching MRAM. And to make this practical, so there is a concept for toggle MRAM. So when you do the flipping, so you need to do it a two-step. First, you apply the first current. So basically, the two currents. Let's say the I1 to the, for example, to the WWL, and I2 to the BL. You have a little bit of timing difference when you apply those two currents. First, you apply the WWL. So, for example, then this is the initial direction for the magnetic layer, and then after you apply the first current, you flip it a little bit, and then you apply the both currents, then you keep flipping, and then after the first one is withdraw, and the second current will keep moving to the right. So eventually you can flip this. So this is to suppress the half selector problem, because you have a timing difference between the WWL and the BL currents. So this is the concept of the toggle MRAM, and the toggle MRAM hard access. So there is a concept of hard access and easy access. So for the magnet, let's say you have, it's always like this elliptical shape, your magnet. So the magnet will have this so-called hard access and easy access. So hard access is where it's more difficult, hard to flip. If the magnet is pointing to this direction, it's hard to flip because this is kind of stable orientation. And then the perpendicular, this side is like easy access, because if the magnet pointing to this easy access, then it's easy to flip to the left or to the right. It's like a meta-stable point in the SRAM, for example, right? So then this is when you completely switch, you always end up with the hard access along this direction. So with this concept, the first generation field switching MRAM was actually fabricated, and this is the example from IBM. And this is a 16 megabit chip from IBM with this concept. And it was fabricated in 180 nanometer process technology node. This was back in early 2000. That was the advanced technology node at that time, right, in early 2000. And then here, I just want to point out some property of the MTJ, this field switching MRAM. You look at the read current and write current. This number is huge, 80 milliamp to write, if you want to write it in 30 nanoseconds. So the reason is that you rely on the current to generate the field, and then the magnetic field to switch. So it's very inefficient. So this current, red current, does not scale very well. And 80 milliamp is a huge number in terms of the current, and power consumption is huge. That's why this field switching MRAM does not find practical application, because the power consumption is too high and the write efficiency is too low. You generate the field by passing large currents, and that field will help the switching. So the field switching MRAM did not fly. And then the second generation of the STT-MRAM came up. So the concept is called STT-MRAM. So here, the advantage of this STT-MRAM over the field MRAM is the scalability in terms of the currents. As we just discussed, the red current of this conventional field MRAM does not scale, because here you need to apply current to generate the circulating field to switch this one. With the scaling, then you make this part smaller and smaller. Or let's say you make the pitch of this right-word line smaller and smaller. That actually will increase the red current, because here you have less wire pitch. Then to switch this MTJ, you need to apply even more current to generate the circulating field. So actually the current goes up when you scale the volume of this MTJ. This is very bad news for the scaling. For smaller technology node, you need to even apply larger red current for the field switching MRAM. So this is a big challenge. And here we draw the red current as a function of the cell dimension. And the field switching MRAM actually increases the current. But the STT-MRAM have a good scaling trend. Smaller size, smaller current. So the STT-MRAM, the switching mechanism is by passing the current directly through the MTJ stack. You don't rely on the external field, and we will discuss that in a minute. So the STT is good for scaling compared to the field switching MRAM. So what is STT? So STT is a spin torque transfer MRAM, and this was discovered in mid-2000, around 2005. So you look at the trend in terms of the prototype chip. So here the blue ones are the prototype chips for the field switching MRAM. And then starting from like 2005, 2006, then the STT-MRAM demonstrations began to dominate, and the capacity of the chip become higher and higher. So basically, industry already gave up or abandoned the concept of the field MRAM, and now the mainstream is this STT. So STT is spin transfer torque, and this is a current-driven switching. It's not field-driven; it's current-driven. So here again, we have this resistance versus now it's not the magnetic field, now it's a current. So it's very simple. You just pass large enough current to go through this MTJ stack. And then depending on the current direction, if your current is going up, then it's going to flip the free layer to the left. If the current is flowing down, then the free layer will point to the right. So it's very efficient in terms of switching. And let's spend some time to understand the principle of the STT switching. It's a little bit tricky. This depends on the spin-dependent quantum tunneling, as we discussed earlier. So for example, here on the left-hand side, let's look at the anti-parallel to the parallel switching. So that means initially it's anti-parallel state. Here the bottom one is pinned layer. In this example, always pinned to the left. And initially the top layer, free layer, the green one, is pointing to the right. So now we want to switch from this anti-parallel to parallel state. And what we do is to apply current, large current, relatively large current through this stack. This is the right current. So current flowing down, that means actually the electrons are injecting upward. The electron and current direction is opposite. So let's say you have electrons injecting to the structure, and the electrons will have two kinds of electrons, spin right and spin left. Right? So when you inject the electrons from external circuitry, you have both types of the spin left and spin right electrons. So that will be injected to the pinned layer. And then the pinned layer is pointing to the left. And pinned layer is kind of thick. So the pinned layer will have a property to reject the electrons that is pointing to the right. Because this is pinned to the left, that means the available states are pointing to the left. So we have the pinned right, spin right electrons that will be rejected or reflected by the pinned layer. So only the spin left electrons here can go through the pinned layer. And then the spin left electrons will go to the free layer. And then this pinned left electron will insert a torque to move the magnetization of this free layer to the left by this torque force. So because this is pointing to the left, so it tends to move the magnetization underneath to move to the left as well. So you will insert a torque. The spin left electrons will try to move this free layer. So after the switching, then this will move to the left. So that's the principle of the anti-parallel to parallel switching. Because the spin right electrons are blocked or reflected by the pinned layer. Let's look at the right-hand side. This is the opposite, the parallel to the anti-parallel switching. So that means initially we have the parallel states, and now we want to make it the anti-parallel. What we need to do is just to reverse the current. And the current to the up, that means we inject the electrons actually from the top down. So both types of electrons, spin left and spin right, will be injected. And the free layer is kind of thin, so both types of electrons can go through. And then when the electrons meet the pinned layer, as we discussed earlier, the pinned layer is kind of thick. So then the pointing to the right, the spin right electrons cannot go through the pinned layer, They will be reflected back. But the spin left electrons will go through all the way down, because here is all the left. The spin left will pass through. Then the reflected spin right electron will come back to the free layer, and that is the force to generate the torque to flip the magnetization of the free layer to the right, because here is the spin right electrons. So you will see that the anti-parallel to parallel or parallel to anti-parallel switching will have some differences. Will have the asymmetry, because here on one hand you will rely on the turtle through electrons to flip. The other one will rely on the reflected electrons to flip. So typically, I think the parallel to anti-parallel switching will be more difficult. You will need to apply a little bit larger current. So that means when you write 1 and write 0, there will be a symmetry in terms of the write currents for the STT-MRAM. But that's basically the principle of the STT switching. So any questions? Any questions? So today I think we have a very short lecture, so we have to stop here today, and then we will continue in the next lecture after the Thanksgiving for the rest of the MRAM section. All right, so if no questions, let's stop here today. Thank you.